I enter anywhere, leave anywhere? The answer is no, but I can enter and exit anywhere that have the right parity. So if the entrance cube and the exit cubes have opposite parity, then this is actually all of the cases. These four are where the entrance and exit cube are adjacent to each other, and these two cases are where they're opposite from each other, not touching. And that's all the cases with all the rotations and reflections. So once you prove that, the base case is actually really easy to do by induction. You just are essentially pasting all of these things together to make any path. And then we can make any Hamiltonian shape. And then further refinement, any shape becomes Hamiltonian. So that's how we prove zigzags are universal. And this connects together all of these gadgets. There's really two gadgets in this proof. The AI gadgets, there's n copies of that. And the zigzag gadget, there's n copies of that as well. Now there are some details to check here, of course, that the zigzag gadgets can actually navigate around and not cross each other with height 8, and that at the end you can fill all the blank space. If you're just organized about how you traverse each of the AIs and where you put the blank space, I think we just leave some headroom, so you can just go up, walk over to where all the blank space is, just sort of do a scan line traversal. Wherever there's blank space, you eat it up with your zigzag at the end. So what this does is it lets the AIs move around completely freely. There shouldn't be any constraints on how the AIs are assigned to these pockets, because we want every solution to the three-partition instance to work here. And the zigzags let us do that because they're so universal. Cool? So I think that's what I wanted to say about this proof. Double check my notes. There was one other thing which I found a little funny rereading this paper, is why 8? Because we know everything has to scale up by a factor of 4, but and that's all we're doing in some sense. But we do make these. We scale all the AIs by a factor of 8. Not a big deal, but there's a reason for 8. If we just did 4 and say, so we want to go, so this thing gets mapped onto here, and we go out and back and out and back. If we just did it 4 times, we would be arriving at basically the same position in the 4x4x4 block. We would be arriving at the same 4x4x4 block that we started from. That's not good because we can only visit a block once. So this is sort of an interface issue between the zigzag, which is nice and universal. You can always paste 2 of these chains together, no problem. Whereas with this thing, which is not universal, it folds into basically this shape. That's it. So we need to make sure that, we can universally do whatever we want in here, but we need to make sure that when we connect between this zigzag structure and then we paste in one of these and then we come back, that we do that in a valid way from the perspective of this big chunk. So the factor of 8 makes sure that we leave from one 4x4x4 chunk, we come back on a different one, and then it's easy to paste all the paths together. So that is AMPath, yeah.
So I don't quite see that this proves that snake cube is
Right, yeah, there's one more issue, which is this was folding this shape, but we want to fold a cube. Yeah, this is an annoying part of the proof. It's very hard to draw. This is my attempt at drawing it, and yeah, so I will sketch the idea. I'll tell you the first part is conceptually easy, again hard to draw. The issue is forcing this chain of blocks to do anything. And one key idea is if you want to fold, let's say, a k by k by k box, if you have a straight path of length k, there aren't very many places you can put that. I mean, I guess there are still orders k squared of them, but you have to start and end at the beginning and end of the overall cube if you have a full length straight. So the first step we do is take your this is the first step. It's upside down because we're doing things in reverse order. So first thing we do is we take a target cube, and we're basically going to have a lot of really long guys. We'll force you to in a row, and you see that in these kinds of puzzles. You tend to have straights of length 3, like this. These are 3 3s in a row, and we're making a 3 by 3 by 3 cube. So that sort of has to live in, well, can do weird things. But it's relatively restricted. You can do something like this, but then these must be the edges of the cube in that case. So we have a bunch of those and lots of care, and we end up reducing the cube to a box, meaning we cover all of the cube, we're forced to cover all of the cube and leave exactly a box behind. Sort of like what we did when we were doing squares into square. We put a bunch of big boxes that were relatively constrained, and it just left an empty space, which is a box. Here it's actually forced exactly. Then once we have a box, so the box will be this wide, and it will go over this way, but it won't have this sort of fine feature stuff. This will just all be filled in as a box. Then this step that's drawn is to carve out this hub and spoke shape. And that's based on a structure like this, where you have a huge thing, and then a relatively short thing of length about 8t, and then we go down, and then immediately back up, and then over and down and up and so on. And that roughly carves out this structure. Now you have to be careful if this is actually unique. But we have some, this is why we only want the height of this box to be 8. Because then you can't go out of plane very much. And this, while this is short, it's longer than 8 if t is bigger than 1. So you can't have this spoke go up. So it does have to live in a plane. Sounds right. And this is much smaller than huge, so you can't hold it some other way. So that's pretty much forced. And then we have to get rid of the other 7 planes, which we do with really long guys. So, unfortunately, we don't have all of that drawn, so it's especially hard to see. But this is a rough idea of how you start with a box, and you do these sort of infrastructure gadgets to just carve out the shape you want, and then then you go into the interesting part of the chain. This is all at the beginning of the chain, and you show it's forced to do all this, and then we start, say, here with some zigzag, and then an AI gadget, and so on. Easy, right? So, you do see here, I would say, a very algorithmic approach. I mean, this idea of showing that zigzags are universal, they can make any shape, this is something we do in computational geometry all the time. We prove that these folding structures fold into whatever we want. So and we hadn't proved this one before, but we were armed with a lot of algorithmic tools to do this, and that let us do this reduction. So lower bounds, in our case, is really all about designing the right algorithms to give you powerful gadgets like this. That's why this is the class called algorithmic lower bounds. Other questions about snake cubes? Adam? I think we want it to be a multiple of 4 so that it's compatible with the grid. 6? Yeah, that seems cleaner. That way we can predict if we leave on this 4x4x4 thing, we know which one will come back on, whereas if it could be in a half grid position, that would be messy. Other questions? I mean, you might be able to make that work, but the advantage of hardness proofs, because it's not a real algorithm, I mean, it's not an algorithm you want to run, the point is to show this problem is hard, you can be inefficient in lots of places. As long as it's still polynomial, it doesn't really matter, except for drawing the pictures. That's one place where it matters. Alright, that's snake cubes. Going to go on to another packing problem. So we've seen rectangles into squares, squares into squares. How about circles into squares? So this is a real life puzzle where you have these, I think they're water jet cut or laser cut metal discs, and you have to fit them into this box. So these are real life puzzles. That's one motivation. There's a stronger motivation for studying this problem because it's related to computational origami. There's this method called the tree method of origami design, if you're interested in it.